Hi everyone, welcome back. So today we're going to understand the very important topic from the electromagnetic waves, which is polarization. And in polarization, what we will understand first, we will understand what is an polarized light. Unpolarized light. After that, we will move to the linear polarization, and then we'll move to the circular polarization, and finally we will cover elliptical polarization. So basically all the four topics are actually connected, and if you understand this unpolarized light, then you will understand what is linear polarization, then you will surely understand elliptical polarization, and finally you will understand the circular and elliptical polarization. But first, what is important, we'll understand this topic both conceptually, like how light actually behaves when it is linearly and circular and elliptical, and we'll understand it mathematically as well. So basically, from the given as you know from the given solution of the equation of electromagnetic wave, if the solution is given, then we must be able to identify whether it is linear, circular, or elliptical polarized. I'm sure that after watching the video that you will be able to identify whether the given light is linear, circular, or elliptical polarized. I hope you understand the sequence, what we will be going through and how we will be going through. So let's first understand what is unpolarized light. Unpolarized light. So basically, the light or the electromagnetic wave comes from the sun is actually unpolarized. Unpolarized. What it means, it means the propagation direction is one. Wave is propagating in a single direction. Propagation is in a single direction. There is no problem in that. But the electric field, the electric field is oscillating in random directions. Random directions. In xy plane, I'll explain it. What I mean, xy plane, I'll consider here propagation is in a single direction. Let's assume that is the z direction. So basically, wave is propagating in this z direction. So let us say this is the z cap. Now there remains other two axes. One is the x-axis and another is the y-axis. So basically, these x-axis and the y-axis form a plane here. And now the electric field in this plane, always in this plane, because electric field has to be perpendicular to the propagation. This is actually main important property of the electromagnetic waves, that is the electric field must be perpendicular to the direction of the propagation. So electric field will oscillate in this plane, but will oscillate in the random direction. Sometimes it will oscillate in perfect x-axis, sometimes it will oscillate in y-axis, sometimes it will go back, sometimes it will come down, sometimes it will go like this, sometimes it will go like this, sometimes it will go like this. So there are no preferred directions. So I'm showing here the electric field component, not the magnetic field, because polarization we explain from the electric field component, not the magnetic field component. And we know from the physics that a magnetic field has to be perpendicular to this electric field. So electric field, if this is the electric field, then magnetic field will be on the same plane, on the same xy plane, will be perpendicular to it, surely. And if this is the electric field, then magnetic field has to be perpendicular to this. If this is the electric field, then magnetic field will be in such direction so that it would be perpendicular to the electric field. But we're not explaining at the same time, while taking electric field and the magnetic field into consideration. We know that electric field then must be perpendicular to the magnetic field, and both must be perpendicular to the propagation. So what we consider here, the propagation is along the z direction. Then the electric field will oscillate in the xy plane, but in the random directions. in the random direction. It will be oscillating in the whole plane, but oscillating in such a way so that it would be perpendicular to this propagation. And obviously then magnetic field remains, that you have to keep in your mind that magnetic field will in turn oscillate in such a direction so that it will be perpendicular to the both electric field and the propagation direction. But will not explain polarization from the magnetic field, because electric field solely and alonely and explicitly explains the polarization. I hope you understand this point. This is a very important point. There is one more important point. The direction in unpolarized light, okay, the direction and phase of electric field in case of an unpolarized light, okay, changes rapidly. I explained this thing to you, that it changes rapidly and randomly with time. Randomly with time. But don't ever forget that it has to follow this condition always. It has to follow this condition. It doesn't matter how it changes the phase, how it changes the direction, but it has with the time, but it has to follow this property. That is, that is something fundamental in nature of the unpolarized light or any electromagnetic wave. That is to be there. So then what we do, we set a polarizer. We set a polarizer, okay, an instrument, sort of instrument. Then we pass this unpolarized light through that polarizer, and then what we do, we select only one direction of electric field, and blocks all other directions. So basically it depends upon the shape of the polarizer. It depends upon how do we use the polarizer as well. If we'll pass only this component of the electric field that is in the direction of the x-axis. So basically we'll set a polarizer in such a way, we set a polarizer in such a way so that only one component passes. That is this electric field, this one passes, x-axis electric field passes through that polarizer, and all other gets blocked. All other components of electric field gets blocked. So after passing through the polarizer, so that depends on the polarizer. How do we use the polarizer? We may get electric field along x-axis only, or we may get it might oscillate in two directions, maybe x and y. Okay, maybe we use a polarizer in such a way that this component also passes, this component also passes. Uh, let me write it here again. So this is the direction of the propagation, and let's say we allowed this component only. We allowed this component only. So this one is the x-axis and this one is the y-axis. Okay, so basically this is the electric field here. So we use a polarizer in such a way that it blocks all the other electric field that are in the different random directions on the xy plane, but we pass it only this one that is along the x-axis. So we call it as a linear polarizer light. Okay, we'll go into the details of the linear polarizer right now. Or if what we can do, we can pass the two components, like we will pass this component of the electric field as well, this component of the electric field as well, so that two components passed through the polarizer and all other electric field gets blocked. So then this could be the circular one, or it could be the elliptical one. That depends upon the many factors, actually many factors. That depends upon the maximum value, that depends upon the phase. So all these things will be discussed in the details. I hope you understand what I mean. What I mean is that after the polarizers, the light is linearly polarized. First, let's use this term, linearly polarized. In that case, the electric field oscillates in one fixed direction. Okay, it will oscillate in this fixed direction. We use the x-axis. Okay, and then you have in your mind how the magnetic field would be obviously in the y direction that time, because it has to be perpendicular to the electric field. Okay, so electric field point is in the one random direction. we choose here the x-axis, and you know about the magnetic field that is to be there in the xy plane, but see, that has to be perpendicular, and that's there always. Okay, but yeah, let me tell you from the beginning that it has to be the electric field that will decide whether the given light is the linear polarizer or the circular polarizer or the elliptical polarizer. Now we'll explain them one by one in details, how to identify, how to say whether the given light is linear, circular, or the elliptical. So let's go directly to the linear polarization. Linear polarization. So if somebody asks you what is linear polarization, so in this the electromagnetic EM wave, in this electromagnetic wave, electric field oscillates along a fixed along a fixed line or direction. Okay, in a plane perpendicular to direction of propagation. Okay, so basically electric field is, oscillating means that it increases its value, and then its value decreases, it becomes zero, then it increases in the other direction, but only in a single, along single x-axis or single axis. Okay, let's again write this is the xy plane, and let's assume the wave is propagating along the z direction. Then this is the, you know from here it is y-axis, from here it is x-axis. Okay, so let's assume the electric field is oscillating in this direction. So it would be here maximum, then it will decrease, then it will again decrease, then it becomes zero, then it increases in this direction, that again increases in this direction, then increase, becomes maximum, here becomes E naught or minus E naught, here it becomes E naught. Okay, so it is oscillating in the single x direction. Okay, it's going up and down, it's going up and down, and the wave is propagating in this direction. So we say this light is polarized, but it is linear polarized because the electric field is oscillating in a line. Okay, it's the line in which the electric field is oscillating. And again, let me remind you how the magnetic field will oscillate. That obviously that will oscillate along the y-axis. Okay, that will oscillate in this direction. Okay, I'm not, since polarization is wholly and solely decided by the electric field component. Okay, not by the magnetic field component, and we know in the mind how the magnetic field varies. So see, this electromagnetic wave is propagating along z direction, electric field is oscillating along only x direction. Okay, it is actually oscillating means its value is increasing, decreasing. It is first it increasing, then decreasing, it becomes zero. I hope you understand the oscillation. Okay, about the main position, let's say this one is the main position at the center. Okay, but it will be always there. So this linear polarized light we get after passing the unpolarized light from the polarizer. This point is very important. So any electromagnetic wave that we get from the sunlight, we have to pass through a polarizer in such a way so that only one component of the electric field, which is along the x-axis, gets passed through it. Okay, so if you stand here and look at some point on the xy plane, and you look at some point on the xy plane, what you will see, the electric field is going up and down along a straight line. This is the important condition, very important condition. And since we know till now we have understood a lot of electromagnetic waves, so electric field would be given by propagating along z direction. So E naught, and what is the direction of this E naught, or the maximum value, is along x-axis, cos of kz minus omega t. Okay, what it means the electric field is oscillating along x direction, and phase will decide the wave is propagating along the z direction. This z will decide that it is propagating along the z direction. I hope this you understand this point. So if someone asks you what is this light, what is this wave, so it's an electromagnetic wave which is propagating propagating along z-axis, and it is polarized along x-axis. So we say, how do we decide this x-axis? From the electric field component, not from the magnetic field component. And if somebody asks you, can you write the magnetic field from it? Yes, easily we can write magnetic field. So it's a wave actually propagating along the z direction, and magnetic field would be b naught or a naught by c, b naught, and it would be cos of kz minus omega t, and it would be y cap, because it has no other option than to oscillate in the y cap. Okay, it has to oscillate in the y cap in order to follow this condition. It has to get followed always. I hope you understand this point. You can write this bzt as a naught by c y cap, okay, and cos of kz minus omega t, or plus you can write phi here. There is no problem in writing phi initial phase. I hope you understand this point. Let me revise very important point here. The tip of electric field vector in case of the linear polarization traces a straight line over time. If you stand here and look at the tip of look at this point, then you will see that tip of the electric field is tracing a straight line, always along x-axis, like going up and down, going up and down, going up and down. Okay, so polarization, I again telling you, polarization is always decided by the direction of electric field, not by the magnetic field. So if magnetic field would have been along the x-axis, then electric field would have been along y-axis. So direction of polarization was y-axis, not the x-axis. I hope you understand. Let me give you some examples. So let me give you some examples. See, there is important point. It's not always x-axis and y-axis. Maybe electric field is oscillating in between. So maybe let me write it. You have to understand the topic in a depth actually. So maybe this is x-axis, this is y-axis, and this is propagation z cap. So this is x, this is y. Maybe electric field is oscillating in this direction, but traces a line. Okay, that's very important point. It traces a line. It has to be, and it has to be perpendicular to this thing. Okay, one of the examples is like E of zt. It is propagating along z direction, and let me write this is E naught x cap plus y cap divided by root 2, then cos of kz minus omega t. This wave is propagating along the z direction decided by this phase, and it says that it is in between the x-axis and the y-axis. It is oscillating. Electric field is oscillating actually at 45 degree between x and y-axis. So it will make it will make some 45 degree with the x-axis, and it will make 45 degree with the y-axis. But yeah, traces the single direction. I mean single axis or single axis, okay, single linear direction. I hope you understand this point now. So see, this will decide the direction of polarization or propagation. Sorry, this will decide the direction of propagation and electric field direction. This component here will decide, or this unit vector will decide the direction of the polarization. Okay, now we will move to the circular polarization. In circular polarization, the electric field component in circular polarization the tip of electric field here I should write tip of electric field component, tip of the electric field vector traces a circle over time. So the field so electric field actually rotates. Electric field rotates at some angular frequency, at some angular frequency. So basically, if we make this plane in which the electric field and the magnetic field is there, so this is the z direction, propagation direction. This is the propagation, wave is again propagating along the z direction. And now here what happens, if electric field is in this direction at some time, and after some time it will move to this, it will oscillate in this direction, or it will move this direction, or it may move this direction, then it will move this direction, then it goes back to this direction. Okay, or it may go otherwise. First it was in this direction, then it will go this direction, that time it rotates clockwise, then it will go this direction, then it will go this direction, then it will go this direction. So there are both possibilities. So if it was along x-axis initially, then it can move to this y-axis. But remember, it is not z direction. Remember, it is not z direction. It is backwards actually. Why? I hope you understand this, because it has to be on the plane. It cannot move. Like outside the plane. It has to be on the plane. So this is actually, I should make it clear here, because I hope you does not get confused. Actually, don't get confused. So initially, if it is along this direction, then it will go this, then it will go negative axis, then it will go negative y-axis. Okay, so this way it goes anti-clockwise direction. Or what it can do, it can go like this. First it was in this direction, x-axis positive, then it will go negative y-axis, then it comes down on the negative x-axis, then it comes positive y-axis. So it will go like this. But yes, this E naught will be there always. E naught, E naught, E naught, E naught. No magnitude difference. That the tip would be maximum value always E naught. And how do the magnetic field varies? You know that it has to be perpendicular. If this is along the x-axis, magnetic field would be on the same plane in such a way so that it makes 90-degree with it. If then electric field moves in this direction, then magnetic field would be in such a direction so that it makes 90-degree with this electric field, with this one. Okay, so you have to keep into mind the basic fundamental property always. Okay, so that means if you sit on some on y-axis, on z-axis, and you watch a point, you watch at a single value of z, you watch here, you want to see how electric field traces the path, then it traces circular path. Okay, it traces a circular path. You feel like it has covered a circle. Okay, and it is not always that it traces in the 90 degrees. Maybe it will trace this, then it will go this, then it will go this, then it will go this. I showed you the easiest way. The point is that the electric field traces a circle on a plane at a fixed on a fixed value of z. Like if you'll see here, with respect to time, the electric field traces a circle. I hope you understand this point. And what about the mathematics? So you write that time the electric field is propagating along z direction. Then what you do, you write it like this: electric field E naught cos of kz minus omega t. Wait a second, E naught a sine of kz minus omega t. Since this time the electric field is actually oscillating in the two directions. Okay, one x and another y, so it traces in the xy plane actually. So it traces in xy plane. So let me write it x cap, let me write this y cap. So electric field is oscillating in both, in whole xy plane, not only along x-axis or not only along the y-axis. Okay, so that is very important. If we see the magnitude, if we see the magnitude, let me not write the magnitude first, but yes, it is very important. If you write the magnitude of this electric field, this becomes the equation of circle. Let's see how. If this is electric field, we can write this as the Ex x cap plus Ey y cap. So in place of Ex, I wrote E naught cos of kz minus omega t, where Ex is E naught cos of kz minus omega t, and Ey is E naught sine of kz minus omega t. So if you write the Ex square plus Ey square, okay, see here, if you write Ex square plus Ey square, it becomes E naught square. Isn't it? X square plus y square is equal to a square. So it is an equation of circle. Okay, that is we call this as a circular polarized. This is only possible if we have both magnitude is same, this E naught and the E naught. Otherwise it is not possible. If we write here E naught and here write E naught dash, then it's not possible to take this E naught here common. I hope you understand the mathematics. If it's here E naught dash, then we cannot write it in the circular equation. So the thing is that the peak must be same on the both values. Okay, so that's very important thing. So there are actually two things. One is the right circular polarization, that next thing we right circular polarization, and another is the left circular polarization. Okay, I told you how visually you can understand it, but again, sometimes you have the equation and you have to understand from the equation whether it is a right circular polarizer or whether it is a left circular polarizer. Okay, so if electric field rotates clockwise, then it is right circular polarization. If electric field rotates anti-clockwise, then it is left circular polarization. So this we understand from the visualization, but from the mathematics, how do we get whether it is a right circular or left circular? So if there is a plus sign between x and y component, let me tell you how. This is the wave propagating along z direction. So if I write like this, x naught E naught x cap cos of kz minus omega t plus E naught y cap sine of kz minus omega t. Okay, see there is a plus sign between, so it is actually right circular polarization. I'll give it proof why it is right circular. And if there is minus sign, E naught x cos of kz minus omega t minus E naught y sine of kz minus omega t. So here is a negative sign, left circular polarization. Why? I'll explain it in a minute. Okay, but yeah, one thing keep into the mind, that this E naught and E naught must be same in both, if that is equal amplitudes in x and y component. This is the very important. And if you see one important thing, that here is cos and here is sine. So phase difference between the components is always 90 degree. Okay, you have to keep this thing in the mind, that phase difference of plus minus pi by 2 between components, it has to follow. Okay, that is one component should be sine and another cos. That is very important. Then there would be a phase difference of plus minus pi by 2, and if then, and also this amplitude must be same. Okay, then that time it is circular polarization. If plus sign is between, then it is right circular polarization. If negative sign is in between, then it is the left circular polarization. I'll explain it why it is right and why it is left circular polarization. So basically, see, if we have an equation, E equals E naught cos of kz minus omega t, this is x cap, and we have plus E naught y cap cos of kz minus omega t. See, initially we can make a small table here. One is omega t, another is ex, and another is ey. Okay, so let's take omega t as 0. Let's take this omega t as 0. So if omega t is, and what we do, we take the point z is equal to 0, where looking at a point at z is equal to 0. If this is a z propagation, we're taking a very important point here. Okay, this point, we're looking at this point, so z is 0. So let's see what will happen to the equation. We have taken the plus sign here. So see, z is 0, this would be 0 because omega t is 0, this is 0, this is 0, so it becomes 0, cos 0 is 1, cos 0 is 1, so E becomes E naught x cap plus E naught y cap. Sorry, this is sine, there must be some sign, I wrote it wrong. So if this is cos, this must be sine component, sine. Okay, so this will become whole 0, so it vanishes, so this part sustains, so there is E naught, only x component, y component is 0. Now after that we'll take omega t, so this part vanishes, and now we'll take omega t is equal to pi by 2. Okay, so omega t is equal to pi by 2. So see, at same z is equal to 0, at same z is equal to 0, so z is 0, this is omega t is pi by 2, so it becomes cos of minus pi by 2, and here this is 0, it becomes sine of minus pi by 2. Okay, let me write it carefully. E is equal to E naught x cap cos of minus, in place of omega t there is pi by 2, plus E naught y cap sine of, it becomes 0, 0 minus omega t is pi by 2 minus pi by 2. Cos of minus pi by 2 is cos of pi by 2. Okay, x cap, and cos of pi by 2 is 0, that vanishes, into 0 plus sine of minus pi by 2 is minus times E naught y cap. Okay, and sine of pi by 2 is then 1, so E naught, so its value becomes minus E naught. And what is x component? X component is 0 and minus E naught. So what happens actually, if we write here, this is the x and this is the y. Okay, there is this direction, this is the minus y cap, this is the x cap, this is minus x cap, this is y cap. Okay, so initially what is the value when omega t is 0? Is E naught, which is along the x-axis. So this here, this is the E naught. Then after that we got minus E naught, but that to be y cap, that means it is along the negative y cap, so it is along this direction. So basically it moves clockwise, you can see here clockwise. And if you take here the negative sign, let's erase this, and take the negative sign. What will happen, so this negative sign here will combine this with negative sign, and it becomes here positive, so only this value changes, it becomes plus E naught. So that time it becomes plus E naught. So basically it moves from x to directly to y, so it moves anti-clockwise. I hope you understand. You do it, you try it yourself, you'll understand how it is right circular and how it is left circular, whether there is a positive sign between and whether there is a negative sign between. Just check it yourself, just do the mathematics, it's very simple, it's just high school mathematics or maybe lower than that. Okay, and now there is elliptical polarization. I know video got a bit lengthy. Elliptical polarization. So in elliptical polarization, the tip, the tip of the electric field, okay, the tip of electric field vector traces, what it would trace an ellipse. Okay, tip of an electric field vector traces out an ellipse. It traces out an ellipse in the xy plane. Okay, now you got it. It has to be in the xy plane as time progresses. As time progresses. So basically, but remember, but the x and y component has unequal amplitudes. So basically, when I show you here, if let me show you here in new plane. So if the wave is propagating along z direction, so if initially it is the electric field E naught along x cap, and when it will move, it may move clockwise or the anti-clockwise, then it is right elliptical and the left elliptical. But the electric field, amplitude will vary. It wouldn't be E naught. Okay, so let's say it moved clockwise, so it will be along the negative y cap, that is backwards. So this time it wouldn't be E naught, but it would be, let's say, E naught dash. Okay, even though it moved clockwise, but the amplitude is not same. So amplitude of x component and the y component would be different this time, not same, just like in the circular polarization it was like same. So basically, if we write the electric field component in this direction, so it would be E1 x cap. So electric field, just like here, let's write it's E1, and let's write here it is as E2. So E1 x cap cos of kz minus omega t. There would be plus or minus, obviously that would decide whether right or left. Okay, it would be E2 y cap sine of kz minus omega t. I hope you got it. Okay, I hope you got it. If there is plus, it is right elliptical polarization. If there is minus, it is left elliptical polarization. Okay, again amplitudes are different, but one more thing, this phase difference should be there. One has to be cos and other has to be sine. Okay, that is very important. That is very important. Now I'll give you certain examples so that you decide whether it is the linear, whether it is a circular, or whether it is the elliptical polarization, and you can decide whether it is the right circular or the left circular. That depends upon the sign. Okay, so let me give you first example. Let me write it like this: E z t 3 cos of kz minus omega t x cap plus 1 cos of kz minus omega t. Be careful about it. Okay, y cap. If you see here, the electric field is 3x cap 1 y cap. Okay, but there is no phase difference. If you can see here, there is no phase difference. This is cos, this is cos. We can take cos common. Cos of don't say in hurry that we say unequal amplitude, so it is elliptical polarization. Okay, don't get confused. And we see x cap and the y cap. One is x, another is y, so it has to be either circular or the elliptical. And since unequal magnitude, so it is elliptical polarization. No, check carefully. There is no phase difference between these two terms. We can take this common, cos of kz minus omega t. It is 3x cap plus 1 y cap. Can you see it? There is only one cos. So wave is propagating along the z direction, and it is in the xy plane. Electric field is moving in some random direction, but in a linear way. There is no cos and sine involved. I hope you it's just like x cap plus y cap plus divided by root 2. Okay, this is some vector. If you understand the basic physics, x axis, y axis, this is some 3x cap. It is like 3 is like 1, so it's a vector actually here. So it's like oscillating, electric field is oscillating like this along this direction on the xy plane. Okay, I hope you get. Don't say so there is a phase difference. What is the way? Phase difference is 0 and unequal amplitudes. So whenever you see phase difference 0, it has to be linear. Okay, unequal amplitudes. Now answer this one. E z t equals E naught cos of kz minus omega t. Let's say this is x cap plus sine of kz minus omega t y cap. Okay, E naught, E naught. Let me erase this one. Let me write it properly. E naught y cap sine of this thing. Okay, now you see, first there is equal amplitudes, so that only not decides the circular. There has to be phase difference of pi by 2 or plus minus. Here is cos and sine with the equal amplitudes, so it is circular. And if you tell me what is what circular, it is right circular because there is plus sign, so it is right circular polarization, right circular polarized light. Okay, now I'll give you an example from the elliptical one. So E zt equals 3x cap cos of kz minus omega t plus 1 y cap sine of kz minus omega t. If you see here, cos sine phase difference of plus minus pi by 2, but unequal here, so it has to be elliptical polarization, elliptical polarization or elliptical polarized light, and with unequal amplitudes and phase difference of pi by 2, whether it is right, if whether it is right elliptical or left, you have to decide from the sign between the cos and sine component. Okay, so thank you for watching. I hope you understand the topic very clearly.